Hello, it's Dr. Daystorms. In the last chapter, we went over electron configurations. In this chapter, we're going to actually start to see how these are important and the effects that the electrons and the protons have on each other. And so we're going to be talking about periodic trends and issues of that nature. And so today, in particular, we're going to discuss what's called the effective nuclear charge and ionic size. So the goals for today are as follows. First, we're going to briefly discuss the periodic table and how they're arranged, because there's a method to the madness and reasons why it is arranged the way that it is. And secondly, we're going to discuss effective nuclear charge and how the protons affect the electrons, because the protons are positively charged, whereas the electrons are negatively charged. So there is an effect on them. Okay. The elements on the periodic table are grouped accordingly to the way that they exert their chemical properties, or exhibit their chemical properties. And so I'm going to just crudely draw, a periodic table here. We have a periodic table that looks roughly like this. And, if you remember from a couple chapters back, the rows on the periodic table are often called families or groups. It's the same; they're used interchangeably. Whereas those are the columns. The rows on the periodic table are called periods. Okay? And remember, the rows are the n, the principal quantum number. It tells you the n. Even though they typically have the similar chemical properties, they are not necessarily identical within the same family or the same group. Okay? Now, what's amazing is that independently, Dmitry Mendeleev and Lothar Meyer came to the same conclusions about how the various elements, the ones at least that were known at that time, should be arranged. They noticed that approximately, especially in the beginning, about every 8 elements, as you add in another proton, exhibit similar characteristics. So, for example, fluorine, chlorine, and then bromine, they all have very similar characteristics. So the halogens, lithium, sodium, potassium have very similar characteristics. So the alkali metals. And so they set up what we now see as the modern-day periodic table. And even though it's really interesting, the history behind this science, I won't quiz you or expect you to know it or to go into great details. But just realize that each of these families, not including hydrogen, but each of these families have similar but not identical characteristics. So in this chapter overall, we're going to be discussing trends and how these periodic trends occur. And so in particular, we're going to discuss the sizes of atoms and their ions, something called ionization energy, and then finally electron affinity. And these are very important not only for general chemistry, but we're also going to see and discuss trends and things like this that have an effect in organic chemistry, biochemistry, and other forms of chemistry in the future. So let's first discuss, before we go into sizes of atoms, let's discuss something called effective nuclear charge. I want to first just briefly go into, actually let's go with a black background, and discuss hydrogen. So we have hydrogen. Remember, hydrogen has 1 proton and 1 electron. So if we draw its nucleus, and I'm going to make this kind of cartoony, we have a 1 plus charge on the inside. We have n equals 1, so it's got 1 electron, which is negatively charged. So that 1 electron is only feeling the pull of the 1 proton. If we go to helium, which is the next one, remember it's got 2 protons and 2 electrons. So here's the helium nucleus. So it's got 2 protons on the inside, n equals 1 once again. So it's going to have 2 electrons on the n equals 1 orbital level. Now, the 2 electrons themselves are going to be repulsed by each other, okay, because they are both the same charge. However, there's also an attraction to that nucleus, since the nucleus is positively charged. Well, what happens, though, if we go to something that's much larger? Let's say, whoops, I hit the wrong button. Let's go to something like sodium. Okay, sodium itself has multiple electrons and neutrons. And neutrons, but multiple electrons and protons. Its atomic number is 11. So that means it's going to have 11 electrons and 11 protons. So let's do here. We have the 11 protons of the nucleus. Then we've got, let me do different colors. N equals 1, because its principal quantum number, principal quantum number is N equals 3. So that's the N equals 1 energy level. Then we have the N equals 2 energy level. And then finally we have the N equals 3 energy level. Very colorful. Now, there are 2 electrons. Remember, it's the 1s2. Then we have 2s2, which I'm just going to go ahead and draw them right here. And then 2p6. So I'm going to put them all in the same 1, 2, 3, 4, 5, 6, 7, 8. Right now they're all in the same N equals level. So this creates, and then we only have 1 electron all by itself way out here. So now you can imagine, or we can discuss the fact that there is a difference in the distance between the nucleus and that outermost energy level for that electron. First off, all of these electrons on the inside here, on this inner core, the first 2 energy levels, they're going to be repelling each other. And so it's kind of shielding the effect. Yes, there are 11, there's 11 protons on the inside, but the effect on this outermost energy level electron, it's not feeling the effect from all 11 protons because it's being shielded by the 10 innermost electrons. So what is that charge that it's feeling? That's called the effective nuclear charge. Okay, so let me just reiterate here. So anytime that we have a mini electron atom, the electrons are both attracted to that nucleus, but they're also repelled by the other electrons. So this is a little cartoon showing what I was trying to draw before. This is sodium. Sodium does have 11, I probably should use a different color. Sodium does have 11 protons on the nucleus, but the problem is that there are 10 other electrons, the one that looks like the neon core, that's blocking this 1 electron out here by itself, and so it doesn't feel the effect of all 11 protons. So that's called the effective nuclear charge. The nuclear charge that any electron experiences depends on how many electrons are around it, and how many electrons are between it and the nucleus, and also how many protons are inside that nucleus. So there is an equation called Z effective for effective nuclear charge. So Z effective is equal to the atomic number, because that tells you how many protons there are, minus the sigma, which is called a screening or shielding constant. Okay, so usually the screening constant is close to the number of inner electrons. So that's why for sodium we say that the atomic number is 11, and the shielding constant is roughly 10, so that outermost electron feels like only 1 proton is pulling on it. Okay? And in reality, this sigma number right here is a little less than 1, but, little less than 1 for every electron. However, for all intents and purposes, we can say that's roughly 1 for every inner core electron. So that means that this 1 electron right here feels the effect of just 1 proton. So why is that important? And what does that have to do about anything? So let's now just start discussing the size of atoms and the way that they bond. First off, remember there are we've discussed so far two types of bonding. One is ionic bonding between ions. That's when you have a positive charged ion that likes a negative charged ion, and so they get stuck together. We really don't need to talk, that doesn't have to do so much with Z effective. The one that we're really focusing on here in this part of the chapter is on the covalent bonding. Remember, covalent bonding is when they share electrons between two atoms. So this is when atoms share or have shared electrons. So why is that important? Let's imagine that we have, there's a nucleus, so it's positively charged, and here's a nucleus of two atoms that are going to be sharing electrons in a covalent bond. The electrons that they're sharing are in here. Let's say this one has the valence electron, the outermost electron is out here in this outermost level. The one for the second atom, maybe it only has 2. N equals 2 for it. So it's got an electron that's sharing out here in this, in its outermost level, which, remember, the term for the outermost levels are called valence. Valence electrons. So it's really important to know what's called the distance between one nucleus to the other. Because remember, the positive charges here and here will actually repel each other. So there's this idealistic distance that is where the two atoms can share the electrons and are their happiest. Okay? Well, the way to find out what that distance is depends upon the diameter, or technically the radius, of each atom. And so, let me go back here. So, the way to find that is you look at the atomic radius for the first one, which is going to be 1/2 its atomic diameter, if you think back to geometry, and the atomic radius, which is 1/2 of its atomic diameter of the second atom. So that's why the size of the atoms really matter, because overall, that's what constitutes, you add up those two, and that's what gives you this overall bonding distance, this covalent bond distance. Okay, so let's go back and we'll see it with the prettier pictures than what I can draw. So the sizes of atoms, the bonding atomic radius, that's defined as 1/2 the distance between the covalently bonded nuclei, which is just a fancy way of saying, see, this is the radius of the first atom, this is the radius of the second atom, so you add them together and you get the diameter, or the distance, I should say, not diameter, the distance between the two nuclei. So that's why we need to know and understand the trends of the sizes of atoms. So let's just talk about the two trends. I want you to know the trends with respect to the same family or group, and with respect to the same period or same row. Okay? So the easier one of the two is to think about the row of the periodic table. And this should make sense. As you go down the periodic table, the atoms get larger. That's easy, really, when you think about it, it's easy to understand because we have, for example, we've got helium with its nucleus, and it's N equals 1. What does N equal for lithium? I'll put lithium in a different color. There's the nucleus for lithium. It's not much bigger. However, what does N equal? N equals 2 for lithium. So we have N equals 1, N equals 2. So it's going to be bigger. If we look at sodium, hopefully you're understanding this trend. Sodium has a nucleus. It's really not much bigger. Remember, the nucleus is relatively small in atoms. It's the electron cloud, the orbitals that take up most of the size. N equals 3 for sodium. So we have N equals 1, the N equals 2 level, and N equals 3. And so then you can see potassium's 4, rubidium's 5, all the way down to francium, which is 7. So that's why as you go down, once again to reiterate, as we go down the periodic table, they tend to get larger. Now, so that one's relatively easy to understand. The one that's a little bit more difficult to understand is as you go from left to right on the periodic table, they typically get smaller. That's what this little diagram here is showing. Or if you want to think about if they go right to left, they typically get larger. Why is that possible? Or why does that happen? That's because there's an increase in the effective nuclear charge. So, let's just look at a couple of examples in order to explain that. Let's look at, for example, let's compare sodium to chlorine. Well, actually, let's compare lithium to fluorine. So we're going to compare lithium to fluorine. They are in the same row of the periodic table. So N equals 2. The nucleus for each one of these, so for lithium, the nucleus is approximately the same size. So I'm going to draw it like this. These are not drawn to scale. So, inside, lithium has a 3 N equals, Z for lithium is 3. That's the atomic number. Z for fluorine is equal to 9. Okay. Now let's do the energy levels. Overall, remember, N equals 2. So that means we have the first energy level for each one of these. And in that energy level, we have how many electrons can fit in a 1s energy level? It's 2. So we've got electron 1, electron 2. And that's true for both of these. Then we have the N equals 2 energy level. Oh, whoops, I drew the wrong kind. And it's roughly the same distance for both. Hopefully I drew those about the same. How many electrons are in each one of these energy levels? Well, we only have 1 electron left for lithium, but we have 7 left for fluorine. 1, 2, 3, 4, 5, 6, 7. So I said that I drew these roughly the same distance, and so you would think, oh, they're going to have the same. They're going to have the same overall atomic radius, but that's not true. See, I purposely misled you there, because we need to figure out what's called Z effective. Remember, we got to figure out that Z effective. So what is Z effective? Oh, whoops, I did the wrong one again. So what is the Z effective? Sigma for lithium is approximately 2, because there are 2 of these inner shell electrons, or core electrons if you want to think of it. The inner shell electrons for fluorine is also 2. They have the same number on the N equals 1 energy level. So sigma is equal to 2. So now let's figure out Z effective for lithium. It's 3 minus 2, which would be approximately positive 1. Let's figure out the Z effective for fluorine. It's 9 minus 2, so it's approximately positive 7. So what does that really mean? What that really means is this one electron right here in lithium, to it only feels the pull from one proton, or approximately one proton. So it's not being pulled in towards the nucleus as much. Any of these outer shell or valence electrons for fluorine, they are feeling approximately, any of these outer shell electrons for fluorine feel approximately the pull of 7 electrons. 7 protons, I'm so sorry. And so what that means is they feel a lot more protons pulling them in. So if I really draw fluorine to make it really resemble what it should, first of all, let me fix my inner shell. It's going to look something more like this. And once again, this is not drawn to scale, so please forgive me. I'm trying to keep my colors straight. One, 2, 3, 4, 5, 6, 7. So now we can see that the atomic radius, or the atomic radius from the is much smaller. That is the reason why, typically, as you go from left to right on the periodic table, so let's go back. So as you go left to right on that periodic table, it gets smaller and smaller and smaller because that effective charge that the outer shell electrons are feeling is increasing, because instead of, you're not adding any more energy levels to it, but you're adding more and more protons. Hopefully this has helped kind of get a good, basic understanding for what is the Z effective, or the effective nuclear charge on this, because this becomes really important when we start talking about bonding and the effects of ions and so on and so forth. And I'll see you in class. Bye.